In this illustration, we intend to simulate the column buckling analysis for various end conditions in the Abaqus software and then compare the results obtained from the Abaqus software with those gained from Analytical Solution. As you observe in the picture, 4 columns with various end conditions are exposed to axial force, and we intend to calculate the critical load for each one of these cases. The purpose of this simulation is to calculate the critical load using the Abaqus software and Analytical Solution, and then compare the results obtained from the Abaqus software with those gained from the Analytical Solution. First, we will simulate the right column in the Abaqus software, then do the same for the column next to it, and we will simulate the other columns in the Abaqus software in the same manner. I will enter the Abaqus software for simulation. I will click on Create Part. I intend to create geometric shape of the column. I'll select the modeling space as 3D. From here, select Deformable, Via, and Planar. Enter approximate size equal to 5 and continue. I will draw a vertical line. As you observe in this picture, the height of column is equal to 1 meter. Done. In the next step, I will enter Property module. Click on Create Material. The column is made of steel. I will click on General menu, then on Density. The density of steel is equal to 7,800 kilograms per cubic meter. I will click on Mechanical menu, then on Elasticity and Elastic. The Young modulus is equal to 200 gigapascal, and I will enter that equal to 200 multiplied by 10 to the power of 9 Pascal. The Poisson ratio is equal to 0.3 and OK. I will click on Create Section. I will select Beam and then Beam again. Continue. Click on Create Beam Profile. Here select Circular and continue. The cross-section of the column is a circle with a radius equal to 0.02 meters. I'll click on Assign Section, select the column, Done, and OK. In the next step, I will click on Assign Beam Orientation, select the column, Done, and press Enter button, and OK. Here you can observe the three-dimensional form of the column. I will enter Assembly module, click on Create Instance, and OK. I will enter Step module, click on Create Step. Here select Linear Perturbation, then select Buckle and continue. We should enter the number of buckling modes in the number of eigenvalues requested section. I will enter the number of buckling modes equal to 4 and OK. I will enter Load module. As you observe, the bottom of the column is absolutely fixed, and the top section of the column can only move directed at y-axis. Here we should define the boundary conditions of the top and bottom sections of the column in the Abaqus software. I will click on Create Boundary Condition, select Initial Step. Here select Displacement, Rotation, and Continue. I will select the bottom section of the column, Done, and close all boundary conditions of displacement. So the bottom section of the column will become absolutely fixed. In the next step, I will click on Create Boundary Condition, select Displacement, Rotation, and Continue. Close all boundary conditions of displacement except U2. In this manner, moving directed at y-axis would become free. In the next step, I will click on Create Load, select Step 1, then select Concentrated Force and Continue. Select this point, Done, and enter the force equal to 1 Newton. In the next step, I will enter Mesh Module. Click on Seed Part, enter Approximate Global Size equal to 0.005 meters. Click on Mesh Part and Yes. Here I will save the model. In the next step, I will enter Job module. Click on Create Job. The model we simulated here is related to both ends fixed model, the picture of which can be observed here. I will click on Submit. The analysis was done successfully, so I'll click on Result. Here you can observe the modes of the buckling. Here we intend to calculate the value of the critical load. You can observe the value of the critical load here, that is equal to 9.80990 multiplied by 10 to the power of 5 Newton, the value of which can also be observed here. To calculate the value of critical load, you will only need to multiply the eigenvalue by the amount of force. Considering that the amount of force applied in the load module was equal to 1 Newton, the value of critical load would be equal to eigenvalue. Actually, the value of critical load is equal to 9.80990 multiplied by 10 to the power of 5 Newton. Now we want to solve this problem using the analytical solution. We use this formula for calculating the value of critical load, and this formula has been extracted from Mechanics of Materials book, which can be observed here. Here, the formula of the critical load can also be observed. PCR here is the same critical load. E is the Young modulus. I is the second moment of area, and LE is effective length. Here, the Young modulus is equal to 200 multiplied by 10 to the power of 9 Pascal. And here you can observe the formula of the second moment of area. The critical load having been obtained from the analytical solution is equal to 992 171 Newton. And the critical load gained from the Abaqus software is equal to 980 990 Newton. As you observe, the results obtained from the Abaqus software are so close to those of analytical solution. Here we want to calculate the difference between the results obtained from the Abaqus software with those of the analytical solutions. As you observe, the difference between the results obtained from the Abaqus software with those of the analytical solution is equal to about 1.1%, and this indicates that the results of the Abaqus software are so close to those of the analytical solution. In the next step, we intend to change the end conditions of the column and calculate the critical load once again. The bottom of the column is absolutely fixed, and at the top of the column, the hinged boundary condition has been used. Now we should change the boundary condition of the top and bottom of the column in the Abaqus software. The bottom boundary condition of the column would not need to be changed, and all boundary conditions of displacement should be closed, because the bottom section of the column is absolutely fixed. The boundary condition of the top section of the column is hinged, so I will tick off the UR3 option, so that the hinged boundary condition would be provided and the rotation about Z would be allowed. I will then click on OK. I will enter job module. I will click on Create. Click on Submit. I'll click on Result. Here you can observe the modes of the buckling. We intend to calculate the critical load, and the critical load is equal to 5.04207 multiplied by 10 to the power of 5 Newton. And here you can observe the value of the critical load. Here the critical load has been calculated using the analytical solution. There is only a difference in value of effective length as compared to the previous model. Here the value of effective length is equal to 0.7 L, and considering that the length of the column is 1 meter, the effective length would be equal to 0.7 meters. Finally, the critical load having been gained from the analytical solution is equal to 506,209 Newton. And the critical load obtained from the Abaqus software is equal to 504,207 Newton. Here the difference between the results obtained from the Abaqus software with those of the analytical solution is about 0.4%. And this indicates that the results of the Abaqus software are so close to those of analytical solution while being of a good precision. In the next step, we intend to change the end conditions of the column. This time, hinges have been used at the top of the column, and the bottom section of the column is hinged as well. Here we intend to apply these changes in the Abaqus software too. I will enter load module. Here I will free UR3 boundary condition for the bottom of the column. So in this manner, the hinged boundary condition would be provided. In this manner, both at the top and bottom of the column, the hinged boundary condition has been used, and rotation about z-axis is quite free. I will click on Create. I'll click on Result. Here you can observe the modes of buckling. Just like previous model, here we also intend to calculate the value of critical load. The value of critical load having been calculated by the Abaqus software is equal to 2.47344 multiplied by 10 to the power of 5 Newton. Now we intend to calculate the critical load using the analytical solution. The only difference between this model with the previous model is in size of the effective length. The effective length is equal to the length of column and is equal to 1 meter. The critical load having been calculated by the analytical solution is equal to 242 Newton. And the critical load calculated using the Abaqus software is equal to 344 Newton. The difference between the results obtained from the Abaqus software with those of the analytical solution is about 0.3%. As it can be observed, the results obtained from the Abaqus software are very close to those of the analytical solution. In the next step, we intend to change the end conditions of the column once again and calculate the critical load again. This time, the bottom of the column is quite fixed and the top section of the column is free. I will apply the boundary conditions in the Abaqus software. As previously mentioned, the bottom of the column is absolutely fixed, so I will close all boundary conditions of displacement. The top section of the column is quite free, so I'll make all boundary conditions of displacement free. To do so, it is enough that I uncheck all options, which means that this boundary condition I have to remove. Therefore, here I will remove this boundary condition. In this manner, the top section of the column will become quite free. Only the bottom of the column would be absolutely fixed in such a situation. I will enter Job module. Click on Create. Here you can observe the modes of the buckling. The critical load by the Abaqus software is 619.68 Newton. Here we intend to calculate the critical load using the analytical solution. The only difference between this model and previous model is concerning the effective length. Here, the effective length is equal to 2L, and eventually the critical load having been calculated by the analytical solution is equal to 620.10 Newton. And the critical load calculated by the Abaqus software is equal to 619.68 Newton. The difference between the results of the Abaqus software with those of the analytical solution is equal to 0.07%. And as you observe, the results obtained by the Abaqus software is quite concordant with those of the analytical solution. The next point we intend to survey here is the mode shapes of the results gained from the Abaqus software with those of the analytical solution. In these pictures, the mode shapes having been obtained from the Abaqus software have been compared with those of the analytical solution. As you observe, the shapes having been obtained from the Abaqus software are quite concordant with those of the analytical solution. Therefore, we calculated the critical load for various end conditions and then compared the results of the Abaqus software with those of the analytical solution and proved that the Abaqus results are quite concordant with those of the analytical Solution.